Hey my homework students, so today we are going to be talking about one of the most important laws in physics, if not the most important laws in physics, and they are very important. I mean, they are literally, if not the most important laws of all time, and these laws were stated by Isaac Newton, and it is 3 laws that we are going to be discussing today, Newton's laws. So before we get into today's video, I would like you to please hit that like, hit that share, hit that comment, and please tell me what you think about this video. A whole entire mood. So the vlogation. As you already can tell that I wrote inertia and Newton's first law, which are the first things that we are going to talk about in this video. Inertia is the tendency of an object to resist changes. It is the tendency of an object to resist changes. What this means that if an object is standing still or is at a standstill, the object will try its best to stand still and not move because it has inertia. And if an object is moving, it will try to keep on moving at that same speed and resist any changes that will try to speed up the object, slow down the object, or stop the object. So that is what the concept of inertia is about. And then now we go on to Newton's first law. Newton's first law is also called the law of inertia, and it states that an object will continue in its state of rest or moving at a constant speed in a straight line unless a non-balanced net force, a non-zero net force acts on it. So now the key word in Newton's first law is continuous. Is continuous. So now it states that an object will keep on doing whatever it is doing if there is no non-zero net force acting on an object. So if there's no force acting on an object, the object will keep on doing what it is doing. What that means is, if this pen is my object and this pen is standing on my hand, this pen will keep on standing still on my hand with no movement if there is no balanced net force acting on it. And if this pen is moving in a straight line at a constant speed, it will keep on moving if there is no non-balanced net force, no non-zero net force acting on it. Usually objects that are moving, they come to a stop because there is something that resists the motion of an object from continuing from moving at that speed, and that is the non-balanced net zero net force that acts on an object, that brings the object to stop. And in most cases it is the case of friction. Okay, so now we understand that inertia is the tendency of an object to resist changes, and then the first law is an object will continue doing whatever it is doing if there is no net force acting on an object. And then now we are going to go on to net force. So net force, okay, so I'll start by defining what a force is. A force is any push or pull. If I'm pushing something, I'm applying a force on it. If I'm pulling something, I'm applying a force on it. And then the net force is the sum of all the forces that are acting on an object. Net force is the sum of all the forces that are acting on an object. So now, if we have an object over here, and we have a force pulling the object to that direction with a force of 5 newtons, right? This 5 newtons, as you can see, it's an arrow with the head and a direction. So this arrow represents a vector. A vector is an arrow representation of a vector quantity. So now a vector is a representation of a vector quantity, and a vector quantity is any quantity that has both magnitude and direction. Magnitude, which is size, and direction is north, east, south, or west. And then a scalar quantity is any quantity that only has magnitude but has no direction. Some of our scalar quantities are things like mass and time, and then our vector quantities are things like velocity, acceleration, things that have direction and magnitude. That is what we call vector quantities. Now back into net force. So now if I'm applying a force of 5 newtons on the box, I'm going to apply the box to move with the force of 5 newtons. And then now if there's only one force, this is only one force acting. But now if there are two forces, one force coming in this direction, a force of 5 newtons. So now there's a force pulling the object and a force pushing the object. And then now when we bring these two vectors together, we get a total net force of 10 newtons in the direction of motion, right? In the direction of motion. You must always remember to put the direction for a vector quantity. And then let's say that this force was now 5 newtons, but then in the other direction, in the opposite direction, the net force would be 5n minus 5n. The moment we have net forces that are moving in opposite direction, we must choose a positive direction and a negative direction. The one in a positive direction is usually the direction of motion, and the one in a negative direction is the one that opposes the motion. So now we're going to have 5n minus 5n, and then we're going to get 0 newtons, right? And then that is how we calculate net forces. Usually forces that go in the direction of motion are forces like applied forces, and then forces that are against the direction of motion are usually forces like friction. And friction is, we are going to get into it real soon. Then applied forces are all the forces that you apply to an object, and then the resultant is the sum of all the forces that are acting together on an object. And then now we have mechanical equilibrium. Mechanical equilibrium, it means that the net force is 0. Mechanical equilibrium means that the net force is 0. This does not necessarily mean that there is no movement of an object. Well, one situation of a case where the net force is 0 is when the object is standing still. As you can see me now, I am standing still, I'm not moving, so there is no net force on me. That means that I am in mechanical equilibrium because I am not moving. But then now let's say a car is another case where we get mechanical equilibrium is when an object is moving. Let's say a car is moving, and the sum of all the forces acting on the car that is moving is 0, and that is also when we have mechanical equilibrium. A case where we get that is when a car is moving at constant velocity. Okay, when a car is moving at constant velocity, when a car or object is moving at constant velocity, when its speed does not change, it is in constant velocity, all the forces acting on the car or objects are equal to 0. But then now the fact that it is moving at the same speed, and the speed is not changing, and the velocity is constant, it means that the sum of all the forces are 0. So now when an object is at rest, the object is in chemical equilibrium. And then when the object is also moving at constant velocity, the object is also in chemical equilibrium. Okay, then now we're going to go on to a support force. Now the support force is a force that is exerted on an object, right? Is exerted, it is a force that is exerted on an object by a surface that it is in contact with. It is always opposite when we are talking about objects in a straight line. That the support force is also called a normal force. It is always opposite and equal to your weight. when you are standing still or when it is constant. So now in this case, if we're using this pen as an example and we're using my hand as a surface, we're gonna say that the normal force is the force that is exerted by my hand, which is the surface, on the pen, and it is going upward, right? It is going directly upward. So now if we have, so we call that the support force. The support force. So now if we have our object and we have our surface, the object's weight is being pulled down into the earth due to gravity. So now we are going to have weight which is directly down, and then the support force is the force that is exerted by the surface, and it is directly upward. Since it is exerted by the surface, it is going up. So now your support force is going to go up, and there you have your support force, usually written by the letter N. So now when the surface is horizontal and there is no movement, and your object is still, even when there is movement, and your object is on the surface, your normal force will always be directly perpendicular to your weight. And usually your weight and your support force, they cancel each other out, which is the reason why when we are dealing with horizontal forces, we do not take into account the normal force and the weight. The only time when we take into account the normal force and the weight is when we are dealing with vertical motion. And then when support force is only there when an object is in contact with the surface. When I am in the air or when a bird is flying, the bird has no support force, because the bird, it is in the bird like a bird that flies, by the way. When it is in the air, it has no support force because it is in no contact with no surface. And then when I'm jumping up, while I'm up, I have no support force because I'm not in contact with the floor. But as soon as I get onto the floor, then the support force is applied on me, right? And then we have the moving earth. The earth is moving at a distance of a rate of 107,000 kilometers per hour, which is almost like 30 kilometers per second. That is how fast the earth is moving. The reason why we as the people on earth don't feel this movement of earth is because the earth is moving at constant velocity. It is moving at a constant velocity, and which means that it is in inertia. The earth maintains its inertia, and then now it is in chemical equilibrium. That is why we do not feel, we are also moving fast with the earth at the very same time, but then we do not feel this movement because the earth is moving at constant velocity and it maintains its inertia, and it is in mechanical equilibrium. With that said, that concludes our first part, which is Newton's first law. Now we are gonna go into Newton's brings in acceleration. It emphasizes acceleration. Whenever you have forces that are unbalanced acting on an object, you always get acceleration. But when the forces are balanced and the sum of the net force is 0, then there is no acceleration. But then once the forces are unbalanced, or if there's one force acting on an object, then we get acceleration. And then acceleration is what we are going to be talking about mostly in Newton's second law. It is very, very, very important in Newton's second law, okay? And then now we get friction. Newton's law also emphasizes the effect of friction. We have kinetic friction, which is also called sliding friction, and static friction. One thing you should know is that static friction, as you know, static means standing still. Static friction is the friction that has to do with objects that are not moving. So if I'm trying to push this pen and this pen is not moving, then the pen, it does have friction, but it only has static friction. And then the moment I am able to move this pen across the surface and I'm able to push this pen, that means that the pen now moves from static friction to kinetic friction. Then kinetic friction is the friction of motion. Remember, something with kineticness, it means that it has motion, it is moving with motion. And then now, with the moment I am able to move this, we get kinetic friction, which is also called sliding friction. So now we have friction is divided into static and kinetic, right? Into these two. And friction is any resistive force that opposes motion. Friction is any resistive force that opposes motion. And then static friction, it is when the object is being pushed but there is no movement, so we get static friction. Then when the object is being pushed and there's movement, and then the force that is opposing that motion is called kinetic or sliding friction, right? This is also called sliding friction. Yes. And then now, friction does not depend on speed, right? It does not depend on speed. But then fluid friction, which is the friction that is associated with air and water, depends on speed. But friction on a surface does not depend on speed. And it also does not depend on the area of contact, right? And one important factor you should know is that static friction is always bigger than kinetic friction. Why? Because for you to get an object to move, you always have to apply a bigger force than to keep the object moving. And when this is evident, when I don't know if you've ever tried to push a car that is not moving, and then the moment that the force that is required to start the car, to start the car and move the car is very, very, very much bigger than the force that you apply when the car is moving. So like when you try to push the car, it's hard, but once the car is moving, it is so much easier to keep pushing the car. I don't know if you've been in that situation, but that is what happens, and that is one of the emphasis that tells us about kinetic and static friction, that shows us the differences between the two frictions. And then we also get weight and mass. And then weight and mass, they are usually used interchangeably, but now we are going to distinguish the two so that we know which one is which. So we have mass and weight. So mass, your mass is quantity of matter of an object. So mass is also the measure of the inertia of an object. And then weight, it is pretty much the force due to gravity. Weight is usually the force due to gravity. So now we write mass in grams or kilograms, and then we write weight in newtons. So weight is a force. One thing you should know is that your mass is constant everywhere in the universe. Whether you are in Jupiter, whether you're in Earth, whether you're in the sun, whether in the moon, your mass will stay that mass. My mass is 63 grams, 63 kilograms. It will stay 63 kilograms, come rain, come thunder, come sun, come whatever. Whether Jesus comes back, my mass will stay like that. But my weight will change. So weight changes from location to location. Usually on Earth it is the same, but in some locations it is different. And then on the surface of the moon it is different. On the surface of Jupiter it is different. If I was to go to heaven, it will be different. Your weight is different in some parts. And then on the surface of the moon, your weight will be 1/6 than it would be if you were on the surface of Earth. Okay, and then that's that. And now we are gonna get into defining Newton's second law and explaining what Newton's second law is. So Newton's second law states that, like I said, it deals with acceleration. It says acceleration, the acceleration of an object is directly proportional to the net force of an object, and it is in direction of the net force, and then it is inversely proportional to the mass of an object. So what that means is acceleration is directly proportional to the net force. This means proportional, and then acceleration is equal to 1 over mass. Well, it is inversely proportional to mass. But this proportionality means that if your acceleration increases, your net force also increase, and they are both in the same direction. So now if my net force doubles, my acceleration will double. If my net force halves, my acceleration will also halve. And then inversely proportional to mass, it means that if when acceleration increases, the mass decreases. If my acceleration doubles, my mass halves. If my mass halves or doubles, if my mass doubles, then my acceleration halves. So they are inversely proportional to each other. And then we have an equation to represent this. The equation is net force, F net is equal to ma, or acceleration is equal to F net over ma. No, not over ma, what? Over m. Ooh, science almost showed me flames there. So now acceleration is directly proportional to F net, and it is inversely proportional to mass. So now the definition of Newton's second law again is acceleration is directly proportional to the net force, and it is in the direction of the net force, and it is inversely proportional to the mass of an object. When acceleration increases, it means that your force, your overall applied force or overall net force increases, and your mass decreases. Okay, that is what proportionality and inversely proportionality is talking about. And then when we are talking about objects, when we're talking about an object in vertical direction, when an object is falling without the effect of air resistance. Air resistance is a resistive force that opposes motion. Air resistance is a resistive force that opposes motion. So when an object falls without air resistance, it means that your object is in free fall, right? It means that your object is in free fall. And remember that it means that your object is in free fall, and the only force that is acting on an object is acceleration, and the acceleration therefore becomes the force of gravity, and that is what we deal with in that situation. So when in free fall, your acceleration becomes gravity, and that is the only thing we calculate. And then in non-free fall, which is a more practical example, it means that when an object is falling down, there is a resistive force that is acting against the motion of the falling object, and that force is called air resistance or air drag. Okay, so now now your acceleration is not g, right? And remember that F net is equal to ma. Now we are when we are trying to find the acceleration of a free falling object, we are going to say acceleration is equal to F net is equal to ma. Now we are going to break down this F net and then since the object is going down, we are going to take the force of the weight, the force of gravity, as the positive force, which is mg. Then we're going to say minus, and then the force that is resisting this downward motion is called air resistance, which is all called R, and then we're going to have is equals to m. and then we can calculate our acceleration. And then the moment your air resistance is big enough as your weight, when your air resistance balances your weight, the velocity it terminates. So it has no longer velocity, and the velocity becomes constant. And terminal velocity is when air resistance balances the force of gravity and the overall net force on the object is 0. When an object reaches terminal velocity, it means that your acceleration is gone, because to calculate acceleration you must have a net force, and then when these two are equal, it means that your net force will become 0. Let's say your weight was 10. So now if your weight is 10 and your air resistance is also 10, that is 10 minus 10, you get 0 over mass. And if the number on top is 0 divided by a number, you're gonna get a 0. So that is how you reach terminal velocity and terminal speed. And then that is that. So now that is Newton's law. That is Newton's second law. And then now for an object that is moving on a horizontal plane, for you to find your F net, in this case, to find your acceleration, you can say F net is equals to m. And then let's say that you have an applied force of 15 newtons, and then you have an applied force of 15 newtons and an acceleration of 10 newtons, right? So find your so let us put, you have an applied force of 15 newtons, and then you have a friction of 10 newtons, and the mass of your object is equal to 1 kg, right? Now to find your acceleration, you're gonna say F net, you're gonna say the applied force minus friction over m. Your applied force is the force that is going in that direction. You minus it from your friction because they are in opposite motion. So you are going to say 15 newtons minus 10 newtons over 1 kg, and then you're gonna have 5 meters per second squared, which is the units for acceleration. Now you get how you get your acceleration, and so that is Newton's second law. Then now we are gonna go into an almost complicated law, but not really complicated. If you know how the law works, then you are covered and you are sharp, then you are fine. And that is Newton's third law. So that is Newton's third law. States that when object A applies a force on object B exerts a force on object A of equal magnitude but in the opposite direction, right? This states that to every action there is a reaction. So now let me redefine this law again. Newton's third law states that when object A exerts a force on object B exerts a force of equal magnitude but in the opposite direction to the other force that exerted the force. Let me give a practical example. So now, if I'm using my thumb and I'm pushing against the wall with my thumb. So my thumb applies a force on the object of the wall, on the wall, and the wall is the other object. So my thumb is object 1. The wall is object 2. So now I take my thumb and I press on the wall. So what that means that I'm applying a force, which is force 1, on object 2. Object 2 in the same time applies a force back into my thumb. So my thumb is pushing into the wall and the wall is pushing into me. And even if I apply a force with my thumb to the paper, I'm pushing on the paper, but the paper pushes on me too, so we are pushing each other. So now if I'm pushing this, and then another example, if this thumb is pushing this thumb, the other thumb is exerting a force of equal magnitude on the other thumb. Make another example of this law, which is every action there is a reaction. If I have a cannon holding a cannonball, and then I shoot the cannonball out of the cannon. So now when the cannonball is exerting a force on the cannon, and then the cannon is also exerting a force on the cannonball, and then the force that is exerted by the cannon on the cannonball is going to make the cannonball move with a force. So now they're exerting forces of equal magnitude on each other, and the reason why the cannonball moves a greater distance or has a greater velocity is because it has a greater acceleration but a smaller mass. And then the cannonball, it doesn't move that much, is because it has a greater mass but a smaller acceleration, which is in accordance with Newton's second law. So now what that means is your F for both objects are the same, and then now your overall, your forces are both the same, but then the acceleration of the small ball is bigger but the mass is smaller, and then the one of the cannon, the acceleration is smaller but the mass is bigger. So now they are in the same proportion, which gives us the same amount of force, right? And then an example of the wall, with my thumb is pushing on a wall and then my thumb is feeling the pain more than the wall, is because my thumb has a smaller mass but a greater acceleration, but the wall has a bigger mass and a smaller acceleration. That is what has to do with them, with this law. And if I'm jumping down from a high mountain, I'm jumping down to the floor, what forces are being exerted? So since I'm coming down to the floor, I am exerting a force to the earth, to the floor, and then and which causes the earth to pull me down. Then in the same time, I'm also exerting a force on the earth, which is pulling the earth up. The reason why we don't see the earth going up is because the earth is very heavy. It has a greater mass than me, which is why only my movement is seen. But then the movement of the earth is not seen. It is because the earth has a smaller mass, has a bigger mass and a smaller acceleration, and I have a greater acceleration and a smaller mass. That is why we see the movement of me, but the earth also moves too. So yeah, that is Newton's third law. Remember, Newton's first law states that when an object will continue in a state of rest or moving at constant velocity along a straight line until a non-zero net force acts on it. And then Newton's second law states that acceleration is directly proportional to the net force of an object, and it is in the direction of the net force, and it is inversely proportional to the mass of the object. And then the third law states that when object A exerts a force on object B exerts a force of equal magnitude but in the opposite direction to object A, right? And then you must also remember that inertia is the tendency of an object to resist changes in motion, and that covers our topic of Newton's laws. Thank you very much for watching this video. I hope you enjoyed it. I really appreciate it, and good luck on your tests, exams, your studies, and everything else. The next video which will be posted will also be on physics, and I cannot wait to see you again. What is it? What's up? Thank you.